comparisons of series. We look at two tests here to determine whether or not a series is divergent or convergent. The first, direct comparison test, and then the second, limit comparison test. They both use a very similar idea that you want to know something about a known convergent or known divergent series to compare the given series with. Here for the direct comparison, and then also for the limit comparison test, you want to recall the geometric series, P series, also the so-called integral test for convergence or divergence. The direct comparison test says that if you take look at two sequences, if they're both positive, here a sub n is less than or equal to b sub n for all n positive. If you know that the series b sub n converges, that's going to be the known convergent series, then anything less than that must also converge. And so thus the series for a sub n converges as well. If you know that the series for a sub n diverges, anything greater than that must also diverge. So let's look at some problems here. So we're going to compare this compared to the summation as n goes from 1 to infinity of 1 over 2n. And if you think about it, this is the same thing as 1 over 2 times the summation as n goes from 1 to infinity of 1 over n. This is a known divergent P series. So this is you recall we call that harmonic. So if we investigate 2n minus 1, which is less than 2n, if you divide both sides by 2n minus 1, divide both sides by 2n, this implies that 1 over 2n minus 1 is greater than 1 over 2n. Well, this satisfies the so-called direct comparison test. And so what that gives us, and let's look at it from this way, this is 1 over 2n is less than 1 over 2n minus 1. Well, since we know that the series of 1 over 2n diverges, anything greater than that must also diverge. And so we say by the direct comparison test, this series here also diverges. This next one, we want to compare with, if you get rid of that negative 1, this is the summation as n goes from 2 to infinity of 1 over the square root of n. This is also a known divergent P series. Here, notice that P is equal to 1/2. So it's less than 1. And so it's less than or equal to 1 for P. And so we call that a divergent P series. So notice that the square root of n minus 1 is less than the square root of n. Now, how am I getting the next inequality? Well, here what we're doing is dividing both sides by both terms. So we divide the square root of n minus 1 over the square root of n minus 1. This is less than the square root of n all over the square root of n minus 1. That is, this is 1 is less than the square root of n all over the square root of n minus 1. Now divide both sides by the square root of n. So we get 1 over the square root of n is less than 1 over the square root of n minus 1. Well, that's the direct comparison. Now notice that the series that represents a sequence of 1 over the square root of n is a known divergent series. Anything greater than that must also diverge. So by direct comparison, the summation as n goes from 2 to infinity of 1 over the square root of n minus 1 also diverges. Now we come to this one. We're going to compare this to the summation as n goes from 2 to infinity of 1 over n plus 1. This is divergent by a couple of things. One is divergent by the so-called, if it was just the summation of 1 over n, we'll talk about the p-series divergent, but it's also divergent by the integral test. So this is divergent by the p-series test, and also and divergent by p-series test and by the integral test. So let's see. The natural log of n here is obviously greater than 1 for n that's greater than 2. If you divide this inequality by a positive term, both sides by the same term, then the inequality holds. So we have the natural log of n divided by n plus 1 is greater than 1 over n plus 1. That is, 1 over n plus 1 is less than the natural log of n all over n plus 1. Again, the summation of 1 over n plus 1 diverges. Anything greater than that must also diverge. So by direct comparison, the summation as n goes from 2 to infinity of the natural log of n over n plus 1 also diverges. And fix up that word there. I don't know if I made it better or whatever. Let's compare to the summation as n goes from 0 to infinity of 1 over 2 to the n. Well, this is a known convergent geometric series. Now, if you look at here, the natural log of n, you compare this to 2 to the n. This is greater than 2 to the n. And you can look at some of those values if you want. In particular, let's see. So if you have, let's say, 2 factorial, which is 2, this is greater than 2 to the second. Well, that's not greater than. So this is equal to 4. So that's less than. And we'll get a statement here, a mathematical statement, in just a moment. What about 3 factorial? Well, that's 6. What is that in comparison to 2 to the 3? Well, this is 8. So this is also less than. What about 4 factorial? That gives us 24. What is that in comparison to 2 to the 4th? So that's 16. Well, that's greater than. What about 5 factorial? That's 120. That's greater than 2 to the 5th of 32. 6 factorial. It's going to be 6 times 120. That's greater than 2 to the 6th of 64. So it looks like we get greater than when the values here of n is greater than 3. So this is the case for all n greater than 3, and a little bit just above 2 to be exact. Greater than 3. Well, here's 3 factorial, we get 6, and here's 2 to the 3rd, that's 8. So I think it's safe to say definitely above 3. So you get to 4 factorial and beyond, and the factorials become greater than this base 2 raised to the so-called nth power. So if that be the case, so we have n factorial is greater than 2 to the n for n large, right? And particularly for n greater than 3. So then 1 over n factorial is less than 1 over 2 to the n. Well, since we know that the series for 1 over 2 to the n converges, anything less than that must also converge. Since the series n goes from 0 to infinity, 1 over 2 to the n converges, and by the direct comparison we have the series as n goes from 0 to infinity of 1 over n factorial also converges. Well, now let's look at the so-called limit comparison test. Well, the limit comparison test, the theory says that if the two given sequences, a sub n and b sub n, are positive, and if the limit of their ratios is a positive and finite number, then whatever happens to one series, the same nature happens to the other. So if one series is convergent, the other series is convergent. If one series is divergent, the other series is divergent. So the key is on the test of the limit, so that's why we call it limit comparison. So here we compare, if you look at the biggest O here, n divided by n squared is 1 over n, so I compare to the summation as n goes from 1 to n, 1 to infinity of the summation of 1 over n. So we're going to use this limit comparison. So we have the limit as n goes to infinity. We look at this as being a sub n, and we look at this over here as being b sub n. So we have here n over n squared plus 1 all over 1 over n. This is the limit as n goes to infinity. This becomes n squared over n squared plus 1. That limit is equal to 1, where here 1 is indeed a finite and positive number. So if that be the case, we're comparing this to a known p-series divergent series. So if that be the case, then by the limit comparison test, the given series also diverges. Whatever happens to one, the same nature happens to the other, if the limit of the ratio is a finite and positive number. We come here, we compare with, if this wasn't a plus 1, this would be 1 over the square root of n squared, or 1 over n. So we compare this with the summation as n goes from 1 to infinity of 1 over n, and I'm going to equate this with the summation as n goes from 1 to infinity of 1 over the square root of n squared. Since the absolute value of n is defined as the square root of n squared. Right? And so we can use that here in positive, right? In greater than 0. So what that gives us in this limit comparison, we take the limit as n goes to infinity of 1 over the square root of n squared plus 1. That's divided by 1 over the square root of n squared. This is the limit as n goes to infinity of the square root of n divided by the square root of n squared plus 1. This is the limit as n goes to infinity of the square root. This is n squared. N squared all over n squared plus 1. And this gives us the limit as n goes to infinity of 1 all over. I'm going to divide each term by n squared. So let me show you that. N squared over n squared, and this is all over n squared divided by n squared plus 1 over n squared. It's the limit as n goes to infinity. This is the square root of 1 over 1 plus 1 over n squared. This limit of 1 over n squared, that little part there, goes to 0, and so we have the limit is equal to 1. Again, it's finite and positive, and so we conclude that by the limit comparison test, this series goes from 0 to infinity of 1 over the square root of n squared plus 1 also diverges. Because we compared this to a known divergent series, right? This guy right here is a known divergent p-series. Okay, the last one here for this little subpart, n squared divided by n to the 5th is 1 over n to the 3rd. So we compare this to the series as n goes from 1 to infinity of 1 over n to the 3rd. So we got that n squared divided by n to the 5th. This is a known convergent p-series. So we take the limits of the ratio here. The limit as n goes to infinity of 2n squared minus 1 over 3n to the 5th plus 2n plus 1 all over 1 over n to the 3rd. This is the limit as n goes to infinity of 2n. This n to the 3rd is multiplied times the numerator, so it's 2n to the 5th minus n to the 3rd. That's all over 3n to the 5th plus 2n plus 1. This is just finding the horizontal isotope, if you recall from algebra. So if the leading terms in the numerator and denominator, if they have the same exponent, then the isotope or the limit becomes the ratio of the leading coefficients. That's just 2 divided by 3. Again, this number is finite and positive, so whatever happens to one also happens to the other. So since this series converges, then the given series also converges. Converges by limit comparison. Okay. Now, Lastly, determine the convergence or divergence of given series. We can use these tests that's given: the nth term test, p-series test, and integral test, limit comparison, geometric, telescoping, or direct comparison. Now, notice that this series is the same thing as, you can take that n to the 1/3, that's divided by n to the first. So this is the summation as n goes from 1 to infinity of 1 over n to the 1 minus a third. And so that gives you 2/3. Here p is equal to 2 over 3. And since this is less than 1, then this guy diverges so this diverges by the p-series test. Let's look at this one. We can compare with the summation as n goes from 1 to infinity of 1 over 5 to the n. You can use direct comparison or limit comparison. Um, it doesn't matter. If you looked at 5 to the n plus 1 is greater than 5 to the n, and then you would get 1 over 5n plus 1 is less than 1 over 5 to the n, that could work. So notice that 5 to the n plus 1 is greater than 5 to the n here, for n values being positive. So this implies that 1 over 5 to the n plus 1 is less than 1 over 5 to the n. But this guy right here is a known convergent, geometric series. So by direct comparison, this series, as n goes from 1 to infinity of 1 over 5 to the n plus 1, also converges. Now let's be honest. A lot of these you can just see, and you can tell that it's convergent or divergent. But you want to state it. You want to be able to express it in some meaningful way. Notice here that the limit as n goes to infinity of 2n over 3n minus 2 is equal to 2 over 3 is not equal to 0. Then by the nth term test for divergence, the series that's given diverges. This is by the nth term test for divergence. Now let's look at this one. Here I will use again, several of these test that you can apply just to one problem. But since I hadn't used this yet, let's use the integral test. So here we get the integral from 1 to infinity of x over, just let n equal to x squared plus 1 to be squared dx. Let u equal to x squared plus 1. This implies that du is 2x dx, and that gives us 1/2 du. Can represent that numerator, x dx. So we get here 1/2 times the integral from 1 to infinity. I'm going to represent this using u du now. So this is 1 over u squared du. 1/2 du picks up the x dx, right? And then this is u to be squared. So this gives us 1/2 times, take the integral u to the -2 plus 1 is -1 all over -1. Evaluate it from 1 to infinity. So this is -1/2 times 1 over u. And let's evaluate it from 1 to infinity. This is -1 over 2 times u was the x squared plus 1. Let's evaluate it from 1 to infinity. Now when you evaluate this denominator, that x term at infinity, that first part, this is, let's come here. This is -1 over 2 times, if you will, infinity. Well, 1 over infinity goes to 0, and this becomes plus 1 over 2. Evaluate the x at 1. This is 1 squared plus 1, right? So I get 0 plus, this is 1/4. And that gives me 1/4. And so the integral test said that if the limit comes out to be a finite number, then the limit here of the integral converges, and thus also the series that it represents also converges. So since the limit of the integral is convergent, then the associated series also converges. Okay. Well, that should do it. Thank you.